Arnaud?
I'm ready. Thank you, Venice, for this introduction. And I would like to present you the team that has actually developed the SynthRock plugin. The plugin was mainly designed by Bert Brill, our head of research and development at DB Earth Sciences. He has mainly done the overall design, the stochastic module, but also the SynthRock, the heat-cube inversion part. And our panelists today are Bruno Chantry and Hélène Huck. Bruno focused mainly on the creation of the synthetic seismograms and the profile module, while Hélène Huck has generated the fluid replacement algorithm. Now, the SynthRock plugin is a full-featured forward pseudo modeling package within OpenDetect. It consists of two modules, stochastic and profile, that will be presented and demonstrated during this webinar. They can both be used to generate thousands of probabilistic models. Pre-stack and post-stack synthetic seismic generation, cross-part analysis, and heat-cube inversion are also part of the SynthRock plugin, and they'll be shown briefly here. Nevertheless, another webinar will be dedicated to them since we'll concentrate on the modeling part during this webinar. Let me first give you a brief history of what brought us here today. In 1995, Paul de Groot and Bert Brill founded DB Earth Sciences. And 1 year after, they released the DGB's first quantitative interpretation software package, GDI, that already included the pseudo-well simulator. In 2002, most of the GDI features were released into an OpenDetect, the OpenDetect software that is an open source interpretation platform. In 2005, 3 years thereafter, we developed the heat-cube inversion that will be discussed later within OpenDetect, but still using the GDI pseudo-well simulator to provide the input. And two years ago, we started the re-engineering of the GDI pseudo-well simulator into an OpenDetect plugin. And that brings us to more or less now, where at the SAG in 1 month's time, we'll make the first public release of the SynthRock plugin. After this introduction, I'll show you, before jumping to the core presentation of the two modeling modes, stochastic and profile, I'll briefly comment and give a few words on key OpenDetect management that must be taken into account prior to starting working with SynthRock. These are the stratigraphy handling, the working with the various properties, and setting the units of measures within OpenDetect. Then we'll go to a detailed presentation of the two modeling modes, stochastic and profile, and I'll finish this webinar discussing the post-modeling utilities that can be done after the well simulation. These are the generation of the synthetic seismogram, the synthetic to seismic scaling, the synthetic to model crossplot analysis, and the heat-cube inversion. Let me start with the OpenDetect management tools, and that is mainly working with the stratigraphic framework in OpenDetect. You may have noticed already from a few years ago that we have added this stratigraphy that is accessible from the OpenDetect main toolbar, and that consists of a tree of supergroups, groups, formations, members, and types with their corresponding boundaries, top or base. Stratigraphy is also including a number of lithologies, sand, shale, limestone, that may be present in one or another formation. And finally, a stratigraphic framework also contains a number of contents, how we call them, that are, for instance, oil, gas, condensate, that are to be specified for each and every framework, and that will be used by SynthRock during the fluid replacement. The framework, the stratigraphy itself, is complemented by the list of what we call the regional markers, and these are the most important well picks for which seismic interpretations are available. That allows the OpenDetect system to make a bridge between the well picks and to correlate these well picks with a number of 2D or 3D horizons. When you click the first time in a new survey on this icon, you'll get this pop-up window that allows you to choose to either build a stratigraphic framework from the scratch, from nothing, or to select one of the existing framework that we provide with the software. In this example, for now, there are only two default frameworks, a simple reservoir framework and a North Sea stratigraphy. The simple reservoir version is looking like this. You have three formations, the reservoir, the one on top, the one below it, that have all either sands or shale lithologies, and two regional markers, the top of the reservoir and the top of the unit below, which is the base of the reservoir. And that is, in the most simplest cases, all that you need to do if you want to start doing some modeling work in OpenDetect in SynthRock. If you choose to start with the North Sea framework, you will have a much more complete framework where you have a number of supergroups, Cretaceous, Jurassic, Triassic, and that are further subdivided into groups, formations, members. You could go optionally up to the types, so up to 5 levels of hierarchy into your geological stratigraphy. All these formations have one or several lithologies in each subunit, and that is something that you need to specify as part of the framework. Finally, your units, some of the units, from far not all units, have attached regional markers at their top or base that are shown here as names and that are linked to the stratigraphic framework on the right-hand side of the stratigraphy. The two previous examples are provided with the software. However, our goal is to build a much more extensive list of worldwide stratigraphic frameworks. If you are interested to participate in expanding this list, please let us know by sending us an email at info@dgbes.com. Now, in order to finish presenting the stratigraphic framework, I want to show three main icons that will work on when working with SynthRock. The first icon you see here at the top part of the stratigraphy manager is your lithology manager. In this one, you'll see the list of all the lithologies that can be used in the framework. That does not mean that they occur in each and every formation, but if you want to have a lithology in at least one formation, it has to be added on this list. Secondly, the second icon allows you to manage the contents of your framework. In this stratigraphic framework, we have two contents, oil and gas, that can be used for the modeling, and they come with their specific display properties, so a pattern, filling, and a given color, and these are display properties that you'll see being used in SynthRock. Finally, the third icon allows you to start the layer modeling, that is either SynthRock Stochastic SynthRock profile or a very basic layer modeling from within the stratigraphy. There are actually two alternate ways to start SynthRock. You can either start it from the analysis menu, going down to layer modeling and starting SynthRock from here, or you can look for the new SynthRock icon to be found in the OpenDetect main toolbar. These two actions will give you a pop-up window where you can choose to start SynthRock either in stochastic mode or in profile mode. Before going to the presentation of SynthRock itself, I'll finish the OpenDetect management presentation by talking a bit on the layer properties. In the survey manager, you'll find a new line called Layer Properties in version 4.4 of OpenDetect that is popping up this Layer Properties management window. This window consists of two parts. The left-hand side, that is a list of available property types, and the right-hand side, that is a list of usable properties. So for instance, the property type sonic travel time gives us in this example two usable properties, the shear sonic and the sonic. These are two measurements of the same physical quantity. at least in the same unit of measure. And these usable properties are the one you need to provide if you intend to use them as input for any modeling in SynthRock. So if you miss any quantity here, you need to add such a quantity before you start working in SynthRock. And the changes you made here in this list can be saved at 3 levels. They can be saved in a given survey only, for all your surveys, or as a default for your OpenDetect user settings. The properties expand a bit further if you double-click on a given property or use this icon. You can define the property with a name within a set of aliases that we use to find back a common property. You have a display color, you have a typical value range and a typical unit, and a default value if needed, if applicable. I just want to stress that this default unit and the default value are the ones that will be used by SynthRock to provide you default units or values when starting the modeling. And that is especially useful if you work in the stochastic module. You can set these units over here, and that will avoid you to select these units in each and every modeling block during the modeling. What you can also do, instead of providing a numerical value for the default value, you can also provide an equation if you plan not to model this quantity, but always to derive it from other modeled quantities. In that case, this mathematical equation will be taken from your property definition and fed into the SynthRock module. We'll see this later, how it looks, how it works. Now that I have presented the OpenDetect key measurements, I'll go to a detailed presentation of the 2 modeling modes, stochastic and profile. First of all, why do we need pseudo-worlds at all? Well, as part of the support team in the OpenDetect software, I very often get the similar kinds of questions, like what attributes shall be used in order to detune the seismic data, or what is the effect of the fluid content on the seismic response. In this example below, there is a very beautiful amplitude anomaly, and the question is, can we trust this amplitude anomaly as being either a direct hydrocarbon indicator, or at all, is this amplitude anomaly a direct fluid indicator? Because it obviously generates a very bright seismic response, a seismic amplitude response that is laterally coherent, as you can see on this body display. But the answer we nearly always give is that you cannot rely on the seismic data alone to answer to these questions. And there's only one way to properly come back with viable answers, and that is to perform pseudo-well modeling to see if it is feasible at all that a change in rock properties would induce such a change in the seismic response, like the one you see on your data. Then if you decide to go for pseudo-well modeling, you still need to choose, am I going to use the stochastic module of SynthRock or the profile module? Well, actually, those 2 simulation modes have different objectives. The stochastic mode generates 1D realizations of a simulation description. On the other hand, the profile mode generates a 2D profile of interpolated pseudo-wells. The profile mode allows you to create, for instance, thickness models by varying the stratigraphy and/or the hydrocarbon content from left to right. It also allows you to create cross-sections by interpolating one or several wells, and that also includes the possibility to pick the structures in between. The stochastic mode, on the other hand, allows you to generate thousands of pseudo-wells, and that is most often used for seismic inversion purposes. It is such because it allows you to capture all geologic and seismic variations in the target interval into one big family of modeled pseudo-wells. This is an overview of the pseudo-well modeling window of SynthRock. If you are a former GDI user, you might reckon that while you are modeling, you may end up working with 10, 20, 30 windows at the same time. This is a big change that you will see when working with SynthRock. We have concentrated everything that you need to do within SynthRock, within your modeling work, in this single layer modeling window. And that happens in the following order. First of all, you'll need to build your model. So in stochastic mode, the model is built here on the left-hand side, and then when pressing go, you'll generate your pseudo-wells. That is for the stochastic mode. In the profile mode, the modeling is actually done in the same window as we use for displaying the modeled interpolated pseudo-wells that are always displayed at the base of the SynthRock layer modeling window. Finally, the synthetics, zero offset synthetics, will always appear simultaneously to the pseudo-wells on the top of the layer modeling window. At the very top, you'll see a number of tools to control the synthetic generation parameters. That's the next steps that you will perform after the pseudo-well modeling. And the last one, it will be the post-modeling utilities that are gathered in this toolbar, and that this is where you can either launch the crossplot analysis, the huck inversion, or perform fluid replacements. Let me now present you in some more details the stochastic well modeling. This is an example of an empty window, an empty stochastic layer modeling window, where you see more or less nothing. You only see click to add, and if you click right here in the model description part, you'll get this pop-up window where you do recognize the list of the properties we saw in the manager beforehand. And in this extensive list, you have to tick what properties you want to work with during the modeling. In this list, you will choose properties that will be modeled, so to speak, and properties that will be derived from other modeled quantities. And you always need at least to select acoustic impedance, density, and p-wave velocity, because these are the three properties that must be included into each and every model, because we need them for generating synthetic seismic data. Once this is done, you'll see while building your model a description overview in this left-hand side of the window, where you see how your model description is looking like. You have here two modeling units, the Permian Zechstein modeling unit and the Permian Rotligand modeling unit. And not only you see these two big blocks, but you see a thin color-coded line here at the very left that is actually giving a color coding per formation. And the biggest column of colors is a color coding per lithology. So this means that you know that this simulation has one big formation here at the top with a single lithology. Then you go to another formation that has another lithology, and so forth. These are very various formations with various lithologies. That is only a very quick overview of how your modeling is looking like in the first place. If you want to do the modeling itself, you'll actually double-click on either of these two blocks, and that will give you your modeling description window. That is, or will be looking like this. It presents a tree view where you will find everything that is underneath this unit of the framework. Here the Permian Rotligand that corresponds to this big block. And in this tree, you'll see, of course, everything that is included in your stratigraphy, but you're not forced to model everything every time. So, for instance, if we know that there are no sands in the upper you can tick the sands off, and they'll not be present they'll not be modeled at all in this simulation. And the first step you'll need to take when doing a pseudo-well simulation, you need to draw the thicknesses of GeoUnits, and that you can do in two ways. For instance, the top of the Detlingen formation, he is in this example modeled with a fixed number of layers set to 1. That means that the top Detlingen formation will have a single shale unit in all the modeled pseudo-wells. That's one way to do it. Another way that we have in this upper Wechsel-Folge formation is actually to tick off the option fixed number of layers and to draw the thickness of the formation from a given distribution, either uniform or Gaussian, with a given average, standard deviation, minimum and maximum thickness value. If you model a formation like this, then you'll have a formation which in this case will have many individual layers that will be only shales because the sands are off, and where the total thickness is drawn from a normal distribution based on these settings. Now for the many layers that are in such a formation, the description overview is looking like this. So this is a standard description for a single thin sand layer of the upper Wechsel formation. They all have a 1 meter thickness, so that is the blocking size of in this formation. So you can have a block size different in each and every formation. You have a relative abundance for a given lithology. Here there are no shales, so I leave this to 100%. And then you need to give rules on how to draw the values of these logs for each layer to be computed. For instance, the gamma ray will be constant for all pseudo-wells. The lithology code for my sands will be equal to 1 in all sands of the upper Wechsel. The P-wave velocity will always be computed from the sonic log. So is the acoustic impedance that is computed from the density and P-wave velocity. And in here, you do recognize the formula that I have specified in the layer properties definition in the management of the layer properties. So these default equations are read in the manager, layer properties manager, and fed back into each and every block to be simulated, so you don't need to do it by hand all the time. Finally, there have to be some quantities that have that get varying log values, and in this example, these are the density, porosity, and sonic values. In this example, I'm generating the values from PDF distributions, and the PDF distributions most often have to come from somewhere. So by pressing the Set button, you get this window where you have to provide the necessary input for the generation of the density log values. So you would need to select a stored PDF distribution, but most often you won't have a stored PDF distribution to provide density values. That is why we have included this well analysis module, that is this very small icon here, that allow you to extract the one or several log values from one or several real wells loaded in your OpenDetect project. You can do this analysis in a very small interval, and that will extract the data, and optionally you can show the extracted data in a crossplot table window, or you can directly go a bit further and create the PDF from the extracted data. You need to provide min and max values for the logs to be modeled, and that will store, in this example, a 3D PDF distribution containing the necessary input to model density logs, sonic logs, and porosity logs in this formation. So this modeling description is reading one single PDF distribution to provide data for density, for porosity, and for sonic. And that is a display of a 2D version of this 3D PDF distribution. Once the well analysis is done, you have done all you need to do the modeling and the stochastic modeling, and all you need to do now is to press the Go button, and that will launch the creation of here 10 pseudo-wells that are all different, but that are all relying on the same modeling description that we provided on the left-hand side. These wells, these pseudo-wells, are displayed like logs, like color-coded logs, and they can be color-coded either by formation. So that was the color of this line here. So once again, it's taking the color coding of your stratigraphic framework and using it for displaying purposes in SynthRock. So you can do this color coding either by formation or by lithology. So in this example, I have a big halite formation on the top, then a anhydrite. Then going into the Permian, we have mostly shales, and in some of the formations below the top Vostro, we have interbedded sands. The top of the formation is here inserted using a regional marker that is displayed as a thin line on top of the modeled pseudo-wells and as a dotted display in front of each and every seismic trace, zero offset synthetic seismic trace. The last step to do in this stochastic modeling will be actually to decide where to put fluid if we want to model changes in fluid content. In this example, I've decided to add a gas column on the top of the Vostro formation, but not in all wells. Actually, I will input with such a setting a gas column only in half of the modeled pseudo-wells. And where the gas column will be present, it will have a constant thickness of 30 meters. If needed, we could decide to expand this gas column below the Vostro formation, so down into the Epstorf formation, or we could crop this gas column in such a way that it will only be part of, only be within the Vostro formation. After the creation of the fluid column, you will also need to specify a few fluid replacement parameters. So there are a number of units that will be containing potentially this hydrocarbon zone, and we need to specify here that before fluid replacement, so after the simulation we had nothing, we had only brine logs, and that thereafter it will be gas filled. And for each of these lines I can specify, I have to specify a bulk modulus value for the hydrocarbons, for the water, same for density, Poisson's ratio, and optionally also porosity and water saturation. But in this case, porosity and water saturation are provided in the model, so they were not provided here in this window. Then once you have provided the fluid replacement parameters, you can use this toggle button, that is this icon here. You find it back in SynthRock in the utility toolbar here. And by pressing this toggle, you can toggle between the pseudo-wells as modeled according to the simulation description and the pseudo-wells after fluid replacement. And what you see, you can use this option that is presenting with a color coding the gas here in red. Actually, it should be in green according to my framework. So only these wells have a gas column, and we see that the seismic response of these wells is actually changing when pressing this toggle. Okay, actually, we have a larger amplitude anomaly when in the wells with gas than before taking into account the gas effect. I'm now done with the presentation of the stochastic well modeling, and I'll hand over the presentation to Claire that will present us in detail the profile modeling.
Thank you, Arnaud. So this stochastic modeling is based on model. And now we're going to see the profile modeling, which is based on the well data. So it's interpolating and extrapolating from the well data. So first, I'm going to show you the thickness, how to do the profile modeling itself, and then later how to do the fluid replacement. So first thing is to create a wedge model. So for that, I'm just going to show you directly in OpenDetect. So you access Synrock with this icon, and then here, instead of stochastic, you select profile. So this is the window for the layer modeling for the profile. So you don't have the model definition because you don't need it as you are going to use your wells. So first of all, you have to add a well. So when you click on the lower rectangle, there is the first window that appears allows you to select which quantity you're going to use for your modeling. So here I'm just going to use the default ones. In there, I select the position where I'm going to locate the well, which well I'm going to select. I select the logs for each quantity I'm going to use I'm going to model, and then I define the interval, the markers I'm going to interval between which I'm going to display the markers. So here I'm going to just select a very small area, and then I click OK, and that will just appear. So so what I'm going to do is just to create a wedge model. I'm going to just display and modify the pseudo well at the first location. So I just edit the markers, and I'm just reduce the thickness to 36. And then at the end, the same, I edit the marker depth for this specific pseudo well. And I will just make the interpolation between these three wells. So to see better, I can simply zoom this way. Okay. So here you have the synthetic seismic, and here is the quantity display is the density. Can display the markers, selecting from here. So here I see this is my top, the top marker I display, and here is the lower one. So you can see that really you have the increased thickness. If I was, for example, in a real case, and I want to introduce a structure, I want to do something in between, I can also draw the behavior of the marker using this just right-clicking on the window and just start marker-based edition. And that will allow me to, after selecting the right marker I want to edit, to just draw, and that will edit actually the behavior of my marker. So that was only the same well I just moved, but you can also obviously see how it behaves if you display different wells. So here is three different wells, and it's doing the interpolation between the 3 wells. So as I say, you may have something happening between your wells, and you want to change the behavior of the markers. For example, here you see that it's a bit more curved and not than a straight interpolation. So you can actually make it more curvy, like in this one. So they will better match what you actually see in your seismic. So you see the difference between so that's the impedance. So you see the impact of changing the marker geometry. Another very important part of this modeling is the fluid replacement. We have in OpenDetect we are able to do a command contour binning that will allow you to see variation, amplitude variation along contours. That will allow you to detect changes, but it doesn't give you the information what if it's fluid, if it's because of lithology. In the profile modeling, we can actually with the fluid replacement we say what we have and see the impact, so we can actually know and use that as an indicator. Okay. Yeah. So that's the common contour binning panel. So here is it's extracting along a surface, and the amplitude is stacked along contours, depth contours. So here you see that this is the stacked amplitude variation with depth. So it allows you to see contacts. So here and here. And now we're going to see how compare with what we see with using SynthRock. So here you have a well I've already loaded. So it's exactly the same way as I showed you before. So you choose position, put here in position 1, select the well, the quantities, and start and stop for the markers. Here is actually the same well as here, but it has been shifted. To do so, it's when you look at the pseudo well, you have this option to apply a global shift. So here it's by default it's 300 meters. That's actually what we apply. You click apply, and then I will just shift your pseudo well, and I will redo the interpolation between the two. And the more you apply, the more the click on apply, the more you apply the same shift. So once you have designed your two wells, you have to look at to define the contents. So here you have the same icon that you find in the stratigraphy manager. They have to be defined in stratigraphy manager before you can access them from here. So here you define what you're gonna have, the content. So you select, here we select gas. It starts from my top marker, and I define this. I can change the thickness. So here I put 180. So once this is defined, I can actually display the zone which is going to be affected by the change when I'm going to do the fluid replacement. So it appears here, this triangle. So then I can define the parameters for my fluid replacement. So the same icon as in the stochastic modeling. So here I define the content. So the two possibilities. So one is with the when I have gas, and the other when I don't have. If you fill this column, and you can change the fluid replacement direction just clicking on the window on the arrows in the middle. So I can change the parameters for the fluid replacement, so they're already filled. But here the porosity and water saturation are empty. As Arnaud said, is when you have logs, that is gonna. It means that it's just gonna use the value of your logs. But here I don't have, so I'm just gonna fill it myself with a porosity of 20% and water saturation of 20%. So when I will click OK, I will just apply my fluid replacement. I will just calculate. And to apply it, I just click on this icon, which is slightly different. There's not the tool picture on it, and I will apply it on my my two screen. So it's calculating, and yes, it's doing here the simulation for 100 wells. So it's we're calculating for all these speed wells. So here you can see the impact of the change I produced, and here the change in the, so that's the density in the density. If I change the parameters, I will see that this this white spot is gonna change. So for example, instead of 20% of water saturation, I'm going to put 75. Let's press OK, and I will just recalculate. That's recalculating. And actually, this is going to be much less brighter. So soon, for the moment, it's not yet available, but we're going to add an advancement bar, so we can see how much it takes. So here you see that it almost disappeared, and here the difference, the impact is less, much less brighter. You can change and see really you can also switch to the previous view, so without the gas, and that will allow you to compare the two very easily. Here we are. So now I give you for the continuation of the presentation, I give the back to Arnaud.
Thank you, Claire, for presenting to us the profile module in detail. After having presenting the two modeling modes, I'll present you very briefly the post-modeling utilities. First of all, start with presenting to you the generation of the synthetic seismograms. The synthetic seismogram parameters are to be set on the very top part of the SynthRock window. You have here a small icon that allows you to select what quantities are used to provide the P-wave velocity quantity, the density quantity, and the S-wave velocity quantity. You also can set the wavelet and scale the wavelet. That is something we'll see thereafter. And the last icon on the first line will pop up for you the specify synthetic parameters window. At first, it will always appear like this. because that is the setting that was used to generate the zero offset synthetics. These are the synthetics that are always displayed by default when you model pseudo-wells for the first time by pressing on the Go button. Note that even though they are zero offset synthetics, they do have source and receiver depths that will affect the timing of the events. Now what you can see is that there are two additional types that you can use to generate synthetic seismic in SynthRock. You can use the type pre-stack to generate full CDP gathers, synthetic CDP gathers, to be computed for each and every pseudo-well. Once you have full CDP gathers, you can actually use the tools here on the second line to browse through the common offset synthetics of these synthetic CDP gathers, either using inputting values or using the arrows left and right to go respectively to lower and larger offset values. The last icon finally allows you to pop up one single synthetic CDP gather, either with or without NMO correction, and to browse with respect to the various pseudo-wells. Now this pre-stack data store can be added, so you don't need to choose to have either zero offset or pre-stack. Now you can add this dataset as an additional dataset to be used for viewing purposes. Finally, the third type, which is also outputting post-stack data that relies on a pre-stack data store, is to actually create a partial offset stack from the pre-stack data store. In order to do this, you have the same parameters as for the pre-stack, but the offset range will actually be the stacking range in order to generate this post-stack attribute. Once again, this synthetic dataset can be added in addition to the existing dataset, and they'll all be present in this view menu where you'll be able to toggle between the various datasets you have. And that is not something you can only use for displaying purposes. These various datasets will also be the ones that will be available later on when working in the crossplot analysis tool or when performing the heat cube inversion. Before I go to the scaling, I just want to give a small warning, because the generation of the pre-stack synthetic gathers implies that the model pseudo-wells start at the surface. Otherwise, the incidence angles at target level will not be correct. As a result, the modeling simulation will need to be changed prior to the ray tracing in order to add an overburdened VPVS and density model. Also, the S-wave velocity will be computed using Castaner's equation if this property is not present in the model. And actually, you could use this option to compute the S-wave quantity using other methods available from the rock physics library. After having specified the synthetic seismic datasets you wish to have, you may need to scale them prior to the crossplot analysis or the heat cube inversion. In order to perform a synthetic to seismic scaling, so to get synthetic seismic traces that have the same amplitude level as your real seismic survey, you can press on the scale button, and that will give you this scale synthetics window. So this window will extract data from the volume in a given time window. So here 0 to plus 48 milliseconds relative to this horizon, so to this level. And that will give you a histogram of the RMS values for the 101 synthetic seismic traces and the histogram of the RMS values extracted from all the real traces from the volume. And on this histogram, you can either pick interactively or use the slider to get the maximum of the histogram distribution. And the scaling factor is nothing less than the ratio between this factor and this factor. We will not store the scaling factor as such. Instead, what we have implemented in SynthRock is that we'll use this scaling factor to be applied on the initial wavelet used to create these synthetics, and will save a scaled wavelet that will be such that if you recreate your synthetic seismic dataset with this scaled wavelet, you'll have directly the right amplitudes. One of the two key post-modeling utilities that you may want to perform is the synthetic to-model crossplot analysis. The window that you pop up from the SynthRock window is looking like this one, and is more or less has three parts. The top part is where you can recognize the standard attributes you see in the normal attribute set window. These attributes will have the same parameters and will be applied to the either the post-stack or the pre-stack synthetics that you have defined previously. The second part of this window allows you to specify attributes that will be computed on the pseudowells, either on the layers of the pseudowells, if you want, for instance, to get a layer thickness, or on the logs if you need to have to get an acoustic impedance log or an average porosity map, for instance. The extraction will always be done with respect to a given reference level. Optionally, you can snap this reference level to an event, a given seismic event prior to the extraction. And the extraction window by default is equal to 0, 0. If you use such an extraction window, you will make grid quantities because you'll only get one output point for each pseudowell. If you use any other time window, then you'll make a volumetric analysis and you'll get many points for each pseudowells, for all pseudowells. And when you press go, you go to this very standard crossplot table window, which is very standard with what you know from the standard OpenDetect crossplot table window. The only additional attributes that you will see if you do a crossplot analysis within SynthRock is that you'll always get the model index, so the index from 1 to n of the pseudowell where this data point was extracted. Otherwise, you still have the x and y values, although it's a bit irrelevant for modeled pseudowells. You have the travel time, the depths, your seismic-based attributes, and your layer-based attributes in this table. Finally, I'll present you the last post-modeling tool, and that is the heat-cube inversion, which is an inversion tool we have developed for 7 years now. What does it do in a nutshell? Well, you see on this slide a standard UVQ waveform segmentation result. In the waveform segmentation workflow, we cluster the seismic waveforms into a number of class centers of representative waveform shapes, and we color code the most likely waveform shape with respect to the actual waveform at every trace in the segment map that you see here. So you get a color-coded map, which is most often showing lateral changes in fascia, so either in terms of structure or hydrocarbon content or lithology. But the main issue with such a UVQ result is that this is as far as you can go with a UVQ segmentation, with a waveform segmentation. You cannot go beyond this map and this display of the class centers. The heat-cube inversion is an attempt to go a bit further and actually to use this information. And what we're doing in the heat-cube inversion, we'll take the actual waveform at each and every seismic trace, so waveform something like this, and we do interrogate the pseudowell database to look for the one pseudowell or the several best pseudowells that have the best match between the actual waveform and the waveform at the same location in the modeled pseudowells. If we find a relevant match, then what we'll do, because we have pseudowells, we know what rock property distribution. So this is a porosity log that corresponds to this modeled pseudo-well waveform. What we do, we use the rock property distribution to take it back into the seismic volume and to back propagate the rock property distribution by looking at the match between the actual waveform and the best fitting pseudo-well. And that allows us to go much further and to make such porosity maps inverted from the seismic waveforms only, using the pseudo-wells as a database to provide a link between the seismic reflectivity and the rock properties. This example has been made for a map, but we could just as easily output a very small porosity distribution in this time gate along the reservoir. In conclusions, I would like to say that the OpenDetect SynthRock is a plugin that is to be used to link your geology with the seismic response. It enables you, for instance, to translate DHIs into rock property variations to know if they are related to stratigraphic changes, lithology changes, or fluid content changes. SynthRock is a modern interactive modeling package that benefits from all the experience of its predecessor GDI. While being quite complete, it should still be noted, however, that the first release will not be as complete as the 16-year-old GDI well simulator. However, it does take advantage of being part of the OpenDetect interpretation platform, as you can see with the stratigraphic tools, with the 3D waveform segmentation tools, and so forth. What can you expect as from today? Well, we intend to make the first release of the SynthRock plugin in early November, in about a month from now, at around the SCG time, to the public. The sponsors will receive an early beta release this week, together with the patch C of OpenDetect 4.4.0. The development of SynthRock is not over now. Many features will be added in the future, and as a result, your feedback is important to let us prioritize these developments. Just a small word on the webinar details. This webinar is recorded and will be available as a video on the following link in a few days. So it's on our website, dgbes.com. Going into the tutorial videos webinar webpage will give you the link to this video. The OpenDetect software can be downloaded at this URL, opendetect.org, at download.html, and evaluation licenses can be requested by email at info@dgbes.com. I just want to thank you now for your attention during this webinar, and all that is left for me is to say happy retirement for GDI, and to welcome SynthRock into our OpenDetect plugin family. Thank you. If you have questions, please feel free to raise your hands.
Okay, thank you very much, Arnaud and Claire. And now it's the time for a Q&A session, so please feel free to do that. Karen, your turn. Go ahead.
I don't want to start all. I really enjoyed the presentation, and I think you created an excellent tool here. And I used to work with GDI Well Simulator, and I really enjoyed that as well. But happy retirement sounds good. Hopefully the full thing will be implemented in OpenDetect, so we get the same user friendliness as we do have in OpenDetect already.
Yes, that is our goal.
I've got a couple questions here. I really like HitCube, and I guess if you combine that with a neural network inversion for certain parameters and compare the results, we could achieve really good interpretation of the subsurface. But by the same thing, we know that the results are not unique, and so I would really like to take my pseudo-well traces and splice those into the 3D cube, so that I can really compare trace by trace more or less. And then I would like to go interactively and change certain parameters of my pseudo-wells to see how it matches the real seismic. Is that possible, or is that too much far-fetched?
Yes, as I said, this webinar was I couldn't slice the Heatcube inversion presentation in this webinar. It would require too much time. But in essence, you'll get a lot of interactivity in the Heatcube inversion, because such a map that you see here will be visible from the SynthRock window as a very quick QC overview of the Heatcube inversion together with the pseudo-well simulation. So you'll have a very quick turnover time between changing a modeling parameter and getting an updated map or inline display of the Heatcube results. Within a couple of minutes, you'll go from your simulation parameters to such maps. So you will be able to see very quickly the effect of your parameters on the Heatcube inverted maps. Also, something I want to mention is that we do not only output the best estimate porosity, for instance, but we also output the standard deviation, because we know that several pseudo-wells will have a very similar match, best fitting match with the actual seismic waveforms. These pseudo-wells, even though they match in a similar way, may have very various porosity distribution, and that is why having access to the deviation in the output rock properties and not only the best estimate is something you can use to QC your Heatcube inversion, so to speak.
I agree, it's a good approach. But I was still wondering, can I now take my synthetic traces and splice those into the 3D cube so that I do have my visual QC, whether I achieved a good test or a match or not?
What you will be able to do, you will be able to output instead of the porosity map, you could output the amplitudes of your synthetic seismic traces. So in this way, you could backpropagate the synthetics back into a 3D volume. Yes. Mm-hmm. Choosing to backpropagate only the best fitting model or the stack of the best 5 and so forth.
Okay, good, thanks.
Any other question from anyone? Okay, I think it was a great presentation and very useful to everyone. And I just want to confirm that we will have a monthly webinar every month, and you will receive a link with that. And as Arnaud mentioned, you will be receiving the recording very soon, by the end of this week. And if you have any questions, please just feel free to contact us or to address your question to webinar@dgbes.com. Thanks everyone, and see you next month.